Hello and welcome to this first exercise looking at a hypothesis test on a single population mean. This one we're going to do is called a one-tail test, so we're just looking at either the upper tail or the lower tail of the distribution, and we're going to start off in the simplest case, assuming that we know what the population standard deviation is. So let's just get into this problem and then we'll kind of walk through what's happening at each step of the way as we go through. So here we have a local craft brewery claims the amount of beer in its bottles is 12 ounces. Now, if we make false claims on the labels, it could result in some serious penalties if it overstates the volume. So we've got a bottle of beer that says it's got 12 ounces in it. We want to make sure that it's got at least 12 ounces in there. Every Monday morning, we take a sample of 30 bottles to test the accuracy of the filling machines. Over the past few years of weekly sampling, we've obtained the standard deviation of the population is 1.6 ounces, and then we have our sample filling volume 11.2 ounces, and we want to know, are we at risk of facing any penalties? So where do we begin? First thing that I always suggest the students do on these problems is go through what can sometimes be a lengthy word problem and pick out the important information. So here I'm going to need this value here because this is our hypothesized value. This is the value against which we're going to be testing this sample mean. So we're going to need that one as well. Here's our sample size, and here's, here's our standard deviation for that population. And over here we have also our level of significance. And what that level of significance is telling us, or telling the reader, whoever's reading the research that we're doing, this is our level of significance. This is how comfortable we are in committing a type 1 error. So this means with alpha equal to 0.05, this means that I am comfortable with a 5% chance of incorrectly rejecting the null hypothesis. So if the null hypothesis happens to be true, I'm comfortable with a 5% chance of accidentally or mistakenly rejecting it. So the first step, formulate the null and alternative hypotheses. So here what we need, here's our null, here's our alternative. Now we're testing a single population mean, so that's just going to be mu as the population mean. Our hypothesized value is given to us right here, 12 ounces. So now the question is, what kind of test is this? Thankfully, we have a clue. It's a one-tailed test. So do I want to test an upper-tailed test or a lower-tailed test? So there's usually hints buried in the question. Sometimes they're easier to find than others. If I look through this, first of all, what is the question asking us? Are they at risk of facing penalties? So that's what I want to test for. I want to see, is there a risk that they will face penalties? Okay, so on what conditions would they face a penalty? Well, we know if making false claims can cause serious penalties if they overstate the true volume. So if in fact the bottle says 12, but the mean filling weight is something less than 12. So what we want to test for is, do we have at least 12 ounces? So my null hypothesis is that we have at least 12 ounces, and our alternative hypothesis is that we have less than 12 ounces, which would imply that the label is overstating the true volume. So this is going to be a lower tail test. Okay, and I'll tell you what that means. Oops, lower tail. When we get around to actually performing the test. That lower tail, that defines what we call a rejection region, or where my test statistic must lie in order for me to reject the null hypotheses. So there we've got our null and alternative. Now to justify this, when I tell my students what this implies, I say, well, what do we learn if we fail to reject? Well, if I fail to reject the null hypotheses here, it means that my evidence supports the claim that the average filling weight is at least 12 ounces, greater than or equal to, so it's at least 12 ounces, so we are not overstating. if my evidence supports the alternative hypotheses, then that implies that we are overstating the true volume. You can think of it overstating, so the label says there's more than there actually is, or we're underfilling. The average filling weight is something, average filling volume is something less than 12 ounces, which is what the label says. So there's our justification, and we're going to perform this test at the 0.05 level of significance. Okay, so I'm just going to write this down because we're going to be coming back to it. Next step, calculate the test statistic. Okay, let me just scribble down some of our other values here so that I can more easily take advantage of them. So, what are we doing? Okay, I have here's my distribution if the null is true, right? We always perform these tests under the assumption that the null hypothesis is true, so true with a mean weight of 12. Sorry, I keep saying weight, volume of 12 ounces. I trust you know what I mean. Now, from this distribution that has a mean of 12, has a standard deviation of 1.6. From this distribution, we took a sample with a mean of 11.2. So let's say that's over here. I don't actually know where it sits. Oops, my goodness, I know better than that though. So let's say we're down here. Something funny going on here. So I'm at 11.2. Now, the next step that we're going to do is identify what is the probability that if this null hypothesis is true, what's the probability of getting a test statistic or a sample value similar to this 11.2 from a distribution with a mean of 12 and standard deviation of 1.6. So what we have to do then is standardize this so that I can compare this now to the normal distribution. So this is our standard normal distribution, mean 0, standard deviation 1. So what we're going to do is just plug our values into our formula, z equals x bar minus our hypothesized value divided by the standard error. And now I'll have over here some corresponding z-score. With that, we can then go to our z-tables and we can find a probability that corresponds with that sample mean. So I'll just do our calculations over here. I'm going to plug in our values, 11.2 minus 12 divided by 1.6 over the square root of, oh, I didn't write down our sample size here. Our sample was 30. So here we go. And now I'll find a calculator here. And let's see, 11.2 minus 12 divided by 1.6 over root 30 equals I'll round that to negative 274. Okay, so I'm going to replace this z. Now I know this is 2.74. So our next step is, what's the probability that corresponds with that test statistic? So what we're going to be looking for in our z-tables is we want to know what's the probability of obtaining a test statistic at least as unlikely as the one that the sample has just provided us. We want the area to the curve, under the curve to the left. And the reason in this case I'm going to the left is because we're doing a lower tailed test. Sometimes if you're not sure if it's lower tail or upper tail, I always tell my students, just look at the direction of the inequality. It's like it's pointing, it's an arrow pointing into the side of the distribution where your rejection region is and where your probabilities are going to be coming from. So a lower tail test, we want that probability in the lower tail. Okay, so here, this is what we're working on now as part C. Use the p-value approach to draw our conclusion. So I've got my test statistic, 274. Here's my messy z distribution with some other nonsense on it from another problem. So 274, let's see. If I look for negative 2.74, and so where those two meet, I have right here that probability 0.0031. And as you can see, these tables, these are giving us lower tail probabilities. So if this is negative 2.74, then this probability is 0.0031. So that's the probability that I want. This area here in this tail, 0.0031. And in this case, that is my p-value. Now that is what we use in order to determine the magnitude of evidence that supports the alternative hypotheses. What that means is that the probability of obtaining a sample mean as rare as this one, 11.2, to get a sample from this distribution, assuming the null is true. If the null is true, the probability of obtaining this sample from that distribution, that probability is very small, 0.003 or 0.3%. So it's possible, right? It's not equal to 0. The probability isn't 0, but the probability is very small. So as much as it's possible, the null might be true, and I still get a sample with that mean. That's possible, but it's so unlikely, as evidenced by this probability. The probability is so small that we can safely say, well, it probably came from a different distribution. Seeing as the probability is so small that it came from this distribution, that means that I'm comfortable saying that it probably came from another distribution. Now, we have a simple rule that we can apply here when we're trying to decide whether or not we're going to reject or not. And that simple rule is that if the p-value is less than or equal to our level of significance, we can reject. So this brings me back to this level of significance up here. That says, well, I'm comfortable with a 5% chance of committing a type 1 error. So that means I'm comfortable with a 5% chance of rejecting this null, even if it might actually be true. So when we come back to our exercise, and I can see that even if that null is true, there's still a non-zero probability that I obtained that this sample came from this distribution. It's still possible. But it's so unlikely that I am going to reject. It's sufficiently unlikely relative to my tolerance towards a type 1 error that I'm going to reject. It's possible that if I reject, I will have just committed a type 1 error because it's possible that it came from that distribution, but my exposure here to a type 1 error is so small, that probability is so small, that by rejecting, my exposure to a type 1 error is less than my tolerance towards a type 1 error. I'm comfortable with a 5% chance. The likelihood that that sample came from that null is exceedingly small. I'll comfortably reject, and so here I have evidence that supports the alternative hypotheses. Okay, so let's move on to the next part, D. Verify our conclusion using the critical value approach. So now this is just a redundant approach to hypothesis testing. Rather than using the p-value approach, which is done here, we can use the critical value approach, where what we'll be doing is just finding a value for z that corresponds with alpha. So what that means is we'll go to our z tables, find the z value that corresponds to an area in this lower tail equal to alpha, and that would then define our rejection space. So in this lower tail test, do I have room right in here? If our test statistic, no, not quite enough room, I'll write over here. If our test statistic is less than or equal to that critical value, then we will reject. And that's exactly the same. We'll always get exactly the same outcomes regardless of what approach we use. So let's just go to our z tables, and we want the critical value z alpha that corresponds with a probability of 0.05. So if we go through this table, now we have to scan this whole body of this table looking for this probability. And the problem with this particular probability is that it's not even actually there, but it's right between these two values here. Right? 0.05 is just right in between here. So our critical value then is going to be negative 1.6, and this is at 0.64, this is at 0.65, and we are right in the middle here, so that's going to be 0.045. So that gives me a critical value of 1.645. So if I come back here, this value is negative 1.645. Here I can see my Z statistic, negative 2.74. Negative 2.74 is definitely less than negative 1.645. So we get the same conclusion, and we reject. So interpret our conclusion. Well, here, both of these methods, well, they always have to give us the same conclusion. I've rejected. I have sufficient evidence to support the alternative hypotheses that yes, we are actually at risk of facing penalties. Our evidence shows that we are underfilling our beer bottles. So that's going to upset probably a lot of people, getting beer bottles that aren't filled properly. So that's all there is to it. It looks a little messy, looks a little bit tedious, but we'll do a few more exercises and get some practice. Okay, I hope that was helpful. Thanks for watching. Bye-bye.